Did it go live? Yes, it's live. Welcome to DevKami number 123. Oops, actually it's 124. My bad. It's actually 124. So I'm Suming.
I am Tristan.
Then we have Sean, our user guest, and also one of my go-to hardware engineer because I'm software guy, etc. So that being said, Wes Shi Leong, he's busy. He has his own thing since the promotion. So apparently I'm the guy with most free time. So yes. So that being said, let's start with our events. The short spoiler, we literally have nothing happening next week. We literally have nothing happening next week. So the next event would be next Saturday and Sunday tech ups on events which you can see outside. Yeah, so that happened. Yes, that's the only events. So let's start with Buzz Corner. So the first one is Deno 1.8 is up. Quite a few interesting feature. So we have this one they have GPU rendering on web GPU, so you can actually implement it to WebAssembly, and you can actually use Deno to actually compile it. So yes, anything want to add on this?
No, haven't tried it. Maybe one of these days.
Yeah. So yeah. So the next one is PyTorch also released 1.8. It's a pure coincidence. One of the things that catch my eyes is the implementation for ROCm. So this is actually the open compute module. Currently, it's mostly run on AMD's graphic card. But for some of us open source user, this is awesome because AMD actually have AMD driver works better for us actually. So it had a much better driver for open source users, and it's actually open source. So which is why on you use Linux, you don't actually have things like Novo or NVIDIA. You just use ROCm and everybody will just accept it. And more importantly, PyTorch is actually one of those big deep learning frameworks. So this is actually a big name, so I'm looking forward to it. I hope that more people actually accept this. So yeah. I know Carrie will, but I don't think he's listening, so there's that. So the next one is Mayastore. This is actually a fast storage for Kubernetes. This actually it works well. So this is actually a new storage system, and this is actually works on top of NVMe and all that. So if you use databases, often when you share all the databases, will actually have problem with storage because everything is shared. It used to be very bad because hard disk actually works on hand. SSD make it better, but NVMe make it even faster because they're actually on PCIe. So with the storage engine, it will optimize this a lot better. But if you don't run your infrastructure, it's very likely to be invisible to you guys. But I'm a nerd, so I like this kind of thing. So anything you want?
Is this Mayastore thing directly to the hardware, or is it still over the file system?
It's I don't know. SPDK. Let me look at. It's storage performance. It's a combination thing. I strongly believe this is a more of an OS level thing. It's something work on top of Linux than to the hardware. So yeah. So it's storage engine for OpenEBS and works with the company's Kubera offering. Yeah, I think it's interesting. So as usual, the links is on DevKami, so if you're interested, you should go on. So the next one is Steampipe. It's a way for you to query API services using SQL. Interesting in a way that Okay, so traditionally when query stuff, you have to write all the logic. SQL, you don't need to, which is awesome. So yeah, I just find it interesting. Anything you guys want to add on this?
What is old is new again?
Yes, I know. The next one is, these are vulnerability already been fixed. So if you get the latest version of Git, you should already have it already. So what happened is, so if you run Git on a file system, that's case insensitive. For example, all the NTFS and all that, and you use symbolic links, with all this, it will cause the script to be executed while cloning your repositories. So it's on Windows or even on Mac OS, you will get this. So the latest update to Git actually will fix this, and you will not have any problem. If you run Linux, it's fine. Run Linux is fine.
And if you don't run Git LFS, LFS is like, I don't know if a lot of people actually run LFS.
Yeah, precisely.
I don't know. At least people just put in like their gigabytes of pictures inside the Git repository. You're not supposed to.
Yes.
But people just do that anyway. So
yes.
I don't know.
Correct. So either way, it's been fixed. Just make sure you upgrade your Git, and we're good to go. Citus had a new rebalancer. This is just an announcement. Citus is actually a provider for PostgreSQL. So they provide all the cool things like columnar storage for size, rebalancer. Probably invisible for most of our guys, but I know some people that actually use it. So yes. So Netflix have yet another orchestration platform. You should check it out if you think it's useful. I didn't evaluate yet. Nowadays, I do some microservices. I still find the whole concept a bit weird, but that's just me. So the next one is supply chain attack, heap pipeline. This actually, we covered this before. It's just that the researcher this time overdo it by actually pushing 4,000 packages over. So the article is essentially saying that we already know the BIS, but what I should look at this article because they actually produce some actionable item. Like don't double check your packages. Make sure your internal packages don't go out just in case. Double check packages. So it's something that we take for granted. So even Python actually have that. So anything we're going to end on this?
This supply chain attack is never gonna end.
No, it's not going to end. So let's say somebody really wants to put things, they can actually do things on, say, Debian repository. If they get access and they manage to get through, it can happen. Then it will affect a lot of Ubuntu boxes. That is also there. Yeah.
A lot of build servers in many companies also are very susceptible to this kind of attack, like because they don't vendor their libraries, right? They pull like basically if you use like 100 node packages, since node seems to be like the end thing. Let's say you have a React application, 100 node packages, and you don't even know what those 100 packages are pulling aside from the ones that you listed, right? And those are all like vectors for attack. Like your surface area is very wide for attacking for this kind of supply chain. So it's a very, I don't know, I guess there just really needs to be a major supply chain attack where people realize we've been doing things really bad all this time. Like the lessons of old are not really learned by the new generation. So there needs to be something big that needs to happen for people to realize, yes, we need to do something.
Yes. So the Python Software Foundation, the PyPy team, PyPI team actually removed quite a few packages when they discovered this. It's not going to be easy because everybody can upload their packages. So it's a proactive thing. So it's not something. It's, well, put it this way, it possibly need to be something like a patrol on the street in the repository to catch something, like the real world, because in the real world, it's precisely what happened in the real world. So, and with that, I think I covered all of the bus corner. You want to know about bus corner and more, join Engineers Mind, Slack. We actually share our news and all that. And occasionally we will put it on our webpage. So that's it. Our topic today is actually continuation of last week, right? I'm going to stop sharing. So in continuation of last week, last week we covered the basics of getting hardware. How do you decide how to work on your project? Where to get components? What basics you need to know and all that. Today is a bit more high level. What is available for you to hack? So, and I'm going to focus on sensors. So, okay, I'm going to, yes.
No, I'll remove myself so that the whole,
yes.
like, you have a larger picture. I think you're going to be showing more stuff, right?
Correct. Okay. So I have, as you see, I have all my stuff
here. Later.
Yes. So as usual, Tristan is busy. I'm the only guy with the free time here. So what is your favorite thing to hack on, Sean? What kind of thing you like to hack?
Well, if you're talking about hardware applications, then I pretty much like microprocessors.
Yeah.
That's what I do. I like to hack on the microprocessor, not the external stuff, the internal stuff. Yeah.
Me, I like to play with the real world. I like to play with the real world because I mean,
the what?
I already said about my history of the real world last time. So which is why I like sensors. So for example, this is a PM sensor from Honeywell. Big name. I might have ruined it by blowing the dust inside. Oh well, it's an accident. Don't blame me. So I like the real world. So, but as a result, I collect a lot of sensors. So for example, this is actually the PM sensor, right? I have, I also have displays. I have a lot of, quite surprisingly, I don't have that many displays actually. So for example, I have, this is an LCD underutilized because I discovered OLED easier to use. So
that's an SPI based, right?
Huh?
SPI based graphical SPI.
Correct. These are SPI based. Then I have. I should show you my photo. Oh well, I lost my photo. This is actually the backup for the soil sensor. This one I get this because there's this time I want to Sina project office at the plant. Nobody wanted the plant. The goal is we put this here, then we connect to an ESP. Then it will shame everybody to water the plant. Yes. So in short, a lot of sensors around. This is all the external one. I wonder why nobody around. I wonder. Oh, there's two people. Then we have, of course, this is, so this one is the micro control package, the whole package. So within it is the sensors, display, buttons all in one. Very cool. Very cool if you're just a software guy and don't care. So that's one. So yeah, what else? Let's see. So yeah, where do we get all this hardware? The short answer is you go to the user online shop. Oh yeah. What else? Oh, okay. I see. I just want to check who is online. That's all. Oh, one watching. Interesting. So where do you get this thing? The short answer is online shop. That's the shop that I showed last time. And what do you mean by that? So for example, we go to my favorite shop. Favorite shop, then we're going to share my tab, blah, 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 share screen, Chrome tab, etc. So this is our favorite shop, and we're going to look at what is available. So for example, you have sensor kits, but sensor kit is really basic. It's really basic. So they have the LEDs, they have the buzzer.
I have the same thing in my office. This one basically all on-off sensors.
Correct. So this is the basic thing for you to learn, which is cool if you're learning, because you got enough to do some interesting things. So for example, you have the temperature sensor. Now you got 1/10 of a weather station in your room. Then what happened is you also have some IR transmitter. So with this, you can actually build aircon controller if you want to, and be smart about it. So you can do some interesting stuff. But then you also have things like individual sensors. You should double check all of these and see what you want. And there's also things that chances is you should really have some idea of what you want to build before go on. Then from there, you should hopefully somebody would actually leave some specification. So for example, Cytron is good in a way that a tendency to leave a lot of detail on how do you actually use a sensor, how do you connect to Arduino and all that. Whereas let's say you go to element 14. Element 14 aim for professional, then they will give you a professional, they will literally give you a professional documentation.
And one big difference between going to, let's say, element 14 and Cytron is that Cytron actually sells you sensor modules. They don't actually sell you the raw sensor usually. Whereas if you want the raw sensor, you actually go to element 14 and that's where you get your raw stuff. Yeah. So it's a lower level.
Yes. So you don't get the type of support that you want. So I'm going to switch the tab. Oh man, it's actually very hard to switch tab. Not to self. Don't do it. Let me switch to my other browser to make things easy. So just know that the professional based shop will actually give you a lot more type, but the integration will not be the same. You will not get so a lot of these that will you have to build your supporting circuit. You have to decide your own interfaces, right? So for example, I give you a very good example. I wonder if I can show this. Let me switch my tab. Stop screen, share screen, application window, sensor. Let me say I can search for Honeywell, right? Honeywell PM. I just want to show example. Then I'm going to show example what Cytron not provide. So there's no good or bad, it's just different. Do they have that?
It's catering to a different market.
Correct.
Honeywell is catering to the companies, industry, and manufacturers, whereas Cytron is catering to hobbies. That's the difference. So different level of support is provided and different level of documentation is provided.
So here's an example of the PM sensor that literally give you this thing, right? They give you this thing. So they literally just give you this. You can see the screen. And you can see the screen, they give you this and possibly the connector. And realize that, and one thing that some of us hobbyists realize that this is not a standard connector for everyone. Meaning you have to build your own circuit very likely. Then they connect to something that is more common. In this case, Cytron provide what we call a growth connector, right? Growth connector. So that's the difference between a professional level shop and these guys. Something to think about. So for software guys like us, probably what you probably want is to go to Cytron first. But you want to explore what is available. Check with element 14, for example. So these are professional shop. Let's give you an idea what you have, and very likely you may or may not get communities that actually works on this sensor to tell you how things work. I wonder if I can see this. So yeah, Cytron sensors. So, and you can do a lot of stuff nowadays. Just remember that you can do a lot of stuff nowadays. Environmental sensors is one of the basic one. Ultrasonic is a bit basic. Then another popular project that people do nowadays is keyboard. It's pretty easy actually, keyboard. What else? What else should I cover? So either way, then camera is actually count as a sensor. In fact, if going through Sean's class, right, chances is even button is a sensor, which is actually true.
Anything that gives you input is a sensor lah.
Correct, precisely. So yes. Then you have output, this one. Then more popular one which I have here is this guy. So this is the I2C one. So yes, a lot of these are very easy to use now. So it's pretty easy to use. Just know that you need to know what is the interface that you need to use for your sensors. That's the main one. So what do you mean? So I'm going to give you an example. Then if I do something wrong, you should actually cut me in because I'm not a professional. I'm just a hobbyist. So let's talk about camera first. Camera is the advanced sensor. Let's go for the basic one. My favorite one, temperature, humidity. So for example, these guys, this is the simplest one around, TO90, M35, right? This is the easiest sensor that you use. You don't have oh yeah, here you are. Where the hell are you doing? Right? You don't have to use serial. You don't have to do a lot of stuff. You do need to communicate, but not a lot. And put this way, the tutorial, just to show you how easy the tutorial is written by an intern student. So it's that easy. So this is actually one of the, so you should double check the interface that they use, where you should connect it. There's a lot of examples. But I know a guy that actually burned this because they flip the output to input differently. I think this is one of the standard student project, right? Is it?
This kind of sensor is fairly simple, but I would have to tell you that nowadays students probably don't play around with this so much because it's an analog sensor. Yeah. Nowadays, people tend to play digital stuff. But just to point out to the listeners here that ultimately every sensor is an analog sensor. Whatever digital stuff you get from it is actually additional processing already. The raw sensor itself is always analog.
Correct. So I give you a very cool one. There is one that is DHT digital. I don't remember. Oh, this is the one I showed us. So this is M35. This is another one. I think this is digital. Yeah, this is also digital. Again, one of those things that we use nowadays. You more likely get this than M35, but when I started, I get M35 actually. So I try to find something that is more advanced interfaces.
The main thing you say is correct lah. That if you are going to build an application, the first question you have to ask yourself is how you want to interface to the sensor lah.
Correct.
Right. So the interfaces you can more or less divide them into certain categories lah. Yep. Right. The analog ones are the most basic, but that will require you to do signal processing on the signal that's coming in, filtering out noise and things like that. So as a result, sometimes people don't need all that. The accuracy of the analog sensor, like for example, you were saying just a temperature sensor. Maybe you just want it to on and off. When the temperature crosses a certain threshold, right, then turn on. If it's below a certain threshold, then turn off. Something like that. So then you can usually buy something like a little module like that has a sensor plus a little bit of extra circuitry to maybe a comparator or something to just turn the thing on, provide you a digital signal, a digital on and off signal. With that is filtered so that you don't need to do all the signal processing on your software side. And you just use a GPIO, read in, on and off, read the value on and off, and that's it.
Yes.
Right. And then of course, then you got the more advanced stuff where you have your SPI, I2C, UART,
Correct.
That will. involve communication protocols.
Correct. And unfortunately, because of this thing, those are the reason why you do not actually have a USB port that plug directly to your sensor to your computer. Because it turns out that despite, even though they use some digital protocol, man, I wish I have a demo. I wish I have a demo for UI. My bad. But either way, even though all this UART protocol and all that is reasonably simple and also digital, but you don't simply just plug it to a computer, because USB actually a very complicated protocol, and you need to tell them that whether it's is it a serial or is it something else. So
USB is a very, very complicated protocol. You need a proper microprocessor with control with USB stack in there.
Correct.
So
which is why you need something like
that. But that said, there have been projects in the past where you can actually Bitbang USB.
Yeah. Okay. So what is Bitbang? Let's go through that, because Bitbang is reasonably. Yeah. So explain Bitbang.
Okay, so Bitbanging is this concept of using your GPIO in a way that it's not meant to be used. A GPIO is basically just a simple pin, an IO pin, like it says, it's general purpose IO. You can use it as an input, you can use it as an output, and you can, if let's say you're using it as an output, for example, you can set it high or set it low, and then if you use it as an input, you can read high or low. That's it. It's as simple as that, right? But the GPIO can also be used to emulate, because it can be set to high and low and read high and low. It can be used to emulate other protocols as well. So if let's say, for example, you wanted to emulate a UART, if you know how the UART physical frame is supposed to look like, right? The ones and zeros, how is it supposed to look like? You can use a GPIO to actually produce those frames or read those frames, either way, like either as an output or input. You can use, let's say you're sending as an output, you can use it to produce those frames, so that on the other side, the receiver, if it's a real UART, it thinks that it's talking to a real UART because the frames that are coming in are actually valid frames. So that's the whole concept of Bitbanging, where you actually use software to try to twiddle the GPIO so that it behaves like some other device.
So the question here is like USB connection. The short answer is yes. So essentially, you try to simulate everything between a computer that can interpret as a USB connection.
Yeah.
So
the USB physical connection is actually very simple. It's only 2 pins, your D plus and D minus, the differential signal, right? And so you only need basically 2 GPIO pins to emulate that. And it is a half duplex protocol, right? So it's fairly doable in software. You send, and then after that you listen, and then after that you send, and then after that you listen. So and then all of the transfer is happening over those 2 pins, and those 2 pins you can set them on and off according to what is needed lah. But of course it's limited. If you are Bitbanging because you're doing it in software, you can't have high speed USB lah. Right, so we are talking about like really low speed USB 1.0 kind of speed, like 1 megabit, that kind of thing lah. Then you can do in software easily lah, or maybe even 12 megabits if you got a higher speed microcontroller. But if you are trying to aim for 480 megabits, then cannot lah. You can't do it.
Yes, precisely. Which is why you always have some form of microcontrollers. I'm so sorry, I have all sorts of toys around here. So for example, even ESP, this is actually like less than 50 ringgit, and they would have a USB controller on board. They would have a USB controller probably here or something, probably here. That's a USB controller. You have a dedicated one for that. So, which is why you do not just buy a sensor. When you buy a sensor set, likely you will need a microcontroller. So a very quick example again, back to my favorite PM sensor. So this thing here is a pig, right? They got a pig that interpret the sensor from here. This thing actually have a pig, hard to see because it's actually this very small thing down here. So they have a PIC to actually interpret the signal and pass it back. So in reality, you would need a microcontroller. You don't actually have a chip. It's very few. It's actually there's actually very few things that actually don't have it. Even the keyboard will have a microcontroller. So we try. Maybe we'll cover microcontroller a bit later, part 1, or maybe you can do it later. So either way, so here's your project. You need to find out what you want to do. That's the first one. Then you need to find out the specification. Then just not already covered that if you go to professional sites, then you're pretty much on your own unless you know what you're doing. If you're actual engineer, that's the place you want to go, because I assume that you are well trained for that. I hope you don't burn down the houses or all that. But if you're a software person, just want to experiment, then you should actually aim for the hobby site. Some of the hobby sites do actually provide some professional hardware as well. Section used to provide the tools for students. Then SparkFun used to have that as well. Then you likely look at Lady Ada to get the inspiration of what you have, right? So that's the first two things. So once you get hardware, then you need to understand the connectivity. So we already covered UART. We already covered I2C. So I2C is the 4 pins one. Put it this way, don't worry about that.
We just mentioned that.
Yeah. Don't worry about that, because as you get the hardware, they will actually tell you that you connect through I2C. And very likely, a lot of these will actually contain documentation to tell you how do you connect it. So for example, you use something that is hobbies friendly, like the Raspberry Pi, bad example. So
maybe I'll just give a very quick overview about the different protocols, right? So that people know, if let's say you have a choice, let's say you have a sensor that has both an I2C and an SPI option, then which one do you buy, right? So there is differences between all the different protocols, limitations and all that, right? Correct. So I just quickly cover. Let's say
you have to share the screen or something.
No, but anyone can just go and Google or Wikipedia if you want to. Yeah. Maybe you can just pull up the Wikipedia page on it. But just give a very quick classification. All right. Yeah. So we have like UART, SPI, I2C. These are the very common protocols, right? So if you are going to classify them, the thing that you will want to look for is the differences in terms of the differences that matter to hardware, basically. Hardware guys is number one, how many pins it takes, because the more pins it's going to take, that means you are losing pins. You need to use more pins on your microcontroller, right? And then the nature of the communication, whether it's duplex, simplex, full duplex, and then also of course the bandwidth, the amount of bandwidth available. Like for example, if you wanted to connect to a temperature sensor, you know that the temperature sensor does not need very high bandwidth because it doesn't change very much, very fast or very often. So a low bandwidth connection would be enough. Whereas if let's say you're connecting to a graphical LCD controller, for example, you will want to have a high speed connection, or maybe don't say graphical, you just want network. You want to connect to Ethernet or Wi-Fi. You need at least a few megabits capable kind of connection. Then you need to know the difference. So the main issue will be number of pins, right? As well as the nature of the communication, whether it's simplex, duplex, half duplex, and things like that, and also the total amount of bandwidth available. Yes. So if we are talking in terms of SPI, UART, and I2C, the fastest will be SPI. Yeah. Right? SPI generally rated, the basic SPI is rated at like 25 megahertz or 25 megabits. Right, so you transfer quite fast, and there's very little overhead in terms of the communication for SPI. There are no additional bits that need to be transferred. It's just transferring the raw data. So that's SPI. SPI is also full duplex. It's full duplex all the time. So you transmit and receive at the same time. So in that sense, also helps because that means you can you sort of double the bandwidth available. Right, transmit and receive at the same time. But the one negative part about SPI is that the number of pins that you need with the number of sensors that grow linearly. So if you basically double the number of sensors you have, you need to double the number of pins that you have as well. Some of the pins of the SPI can be shared, but the slave select pin is not shareable. So you literally need to have, it will grow linearly lah. Every sensor you have has its own slave select, so it's going to grow linearly.
And also when you find, let's say you get an Arduino, for example, you realize that you don't actually have that many of those pins actually. You don't actually have. So for example, if you look at the link that I show you, an Arduino will really have like have like only one SPI, two I2C, and UART. So it's not, these things are not free, and even though it depends on the hardware. So for example, I think ESP actually have more. Everything can be used, but it's something you need to think about. So SPI is one of those. It will grow, and the pins are there's not that many pins as you said on the Arduino, so you will actually grow. So anything else?
The basic SPI needs 4 pins, right? But then the slave select will grow linearly lah. So
and there's a new update, by the way. They don't call it slave select anymore. They call it chip select. And Mozi Maizo, it's serial data out and serial data in. So we have to be politically correct here.
You know the problem with that, what happened was one of the projects that we were working on, one of my staff, he got confused about slave SDI, SDO is which out, which in, and then when he designed the PCB, he actually did it the wrong way. So the 2 outputs were corrected and 2 inputs were corrected. So instead of reworking the whole PCB, we big bang the SPI. so we did a software fix instead of fixing the hardware. But so SPI is the fastest lah. Right. Then the next fastest, we go down one step down, is I2C lah. I2C, we're talking about basic I2C, 100 kilobits, slightly faster, 400 kilobits, super fast. Even the fastest I2C that is going to be used by hobbyists will be only in the range of maybe 1 to 4 megabits. So that's the kind of speed we are talking about on I2C. But when you will realize, when you go and look at the sensors, most of the sensors are running at the original version 1 I2C speed, which is only about 100 kilobits. That is pretty much the speed lah. And there is a slight overhead in terms of the handshaking and transmission of the data. Every byte needs to be acknowledged and things like that. So your 100 megabits, you have to sort of divide by 9. So you don't actually divide by 8, you divide by 9. So that's the amount of bandwidth available. And I2C, unfortunately, is half duplex. So you can either send or receive. You can't do both at the same time. So that makes your bandwidth even lower. So that's why I2C is useful for like really, really low speed sensors, like I said, temperature sensor, for example. You don't need to sample the temperature sensor very regularly. Temperature hardly changes, that kind of thing.
And also, the display don't need that many information anyway. This is the 180.
Assuming that the display has its own frame buffer built in, then you just basically write the information out to the frame buffer, and you only write the updates the frame buffer. If not, your display, if your display is a direct display control, you actually need high speed bandwidth in order to refresh, your refresh rate lah. But one good thing about I2C is that it doesn't grow exponentially in terms of number of pins. It is a bus that was designed specifically for this. So with only 2 pins, I2C only requires 2 pins. Your SCL and SDA, and with those 2 pins, you can connect as many slaves as you want to those 2 pins. In fact, it is also a multi-master bus, so you can actually have multiple masters on the same bus as well. But yeah, you can connect as many as you want, but keep in mind that your bandwidth is limited lah.
Well, you can connect as many as you want, but as long as they don't share the same I2C address. Because every device will have to have its own address lah. But you can't have that many devices anyway lah.
Yeah, in practice, unless you build, in reality, the only time I can think of it when you build a robot, but when you build a robot, you're actually using a very powerful thing with a lot of I/O anyway.
Well, those are like self-contained. Well, I wanted to ask, like, how long would the wires would be for I2C, because you can have like a central, like let's say we do the Stanley's lighting thing, right? Where you have I guess you have a single microcontroller, but your lights and the control of the lights will be everywhere else, and there's going to be animation of the light, and so you have a single controller with multiple microcontrollers for each section of that building. So how long would that be, and how do you make sure that the signal integrity is maintained while you're like daisy chaining throughout all of these microcontrollers?
Well, one advantage or one unique thing about the I2C that is different from the other protocols is that I2C is not driven by the microcontroller. The signal itself comes, the signal itself, i.e. the current, is not produced or not driven by the controller. It is the controller actually just twiddles the signals. The signal, the power, and the current, everything comes external from an external source. Okay, so in that sense, it does help you, because then at least the amount of current you need to supply can be huge. Because if you have, let's say, a lot of devices connected to it and your wire is very long, and you want more responsive things like that, you need more current, right?
So it's basically a pull up, right? So everyone just pulls the signal high, and then whenever the master controller wants to send a signal, it just like pulls it down. Yeah, and which is like easier because I guess like you mentioned, the external power source can keep the whole thing high. So you can have like multiple voltage sources across the whole line, which keeps the line high and doesn't sag. And so what is 1 is like clear to be 1, and then what is 0 is clear to be 0.
And another thing that is another advantage for I2C for long distance is that its speed is very low. It's only about 100 kilobits. So in terms of the amount of time, if you really want to work out what the maximum length of the wire, you can actually work it out, right? You work out 100 kilohertz, i.e. assuming a signal goes switches at a maximum speed, and then you compute the amount of time the speed of an electron, right? Based on the speed of electron flow through, let's say, copper wire, you can figure out what is the maximum length the signal can actually travel within that period, within that 1 bit period. So that you can sort of work out it's kind of a long signal in the range of kilometers.
Are you restricted to that 100 kilobits because you have a clock line, right? So you can basically control the clock. Yeah, you can stretch the thing, and you can even go slower if you need more, like not bandwidth, but you need more data integrity. Like you need to keep it low for longer and keep it high for longer, just so that it actually gets through.
Yeah, clock stretching. I'm just talking about the maximum. Right? So if you're running at 100 kilohertz, right, 100 kilobits, then you can sort of work out that is your distance. But like I say, it's in the range of kilometers. So you are not really whatever you use it for is unlikely to be multiple cities, spanning multiple cities. It's going to be within your house or within the building or within something, right? So it is usable. Yeah. So that's SPI and I2C. So I2C's advantage is only 2 wires, right? So in that sense, it's simple. But disadvantage is lower speed, and also disadvantage lower speed. That's about it, right? Lower speed.
Yeah. Well, each sensor needs to have its own address. Basically, you can have multiple of the same thing.
Yes.
So maximum you can only have is 1,000. Because the addressing is only maximum of 10 bits. Standard is 7 bits, but you can go up to 10 bits. So at maximum, you can have about 1,000 devices on a single bus, addressable from a single bus. But like I said, with only 100 kilobits, if you have 1,000 devices, that's only like 100 bits per device, per second. Is unlikely for that to happen. It's going to be very slow.
The next one that we actually commonly use is actually UART. This is serial.
Yeah, UART.
Yeah.
UARTs are mainly used for machine-to-machine communication. So less for sensors, but your microcontroller to another microcontroller. Usually,
it's used for sending JSON, right?
Yes, you can use it to send JSON. Yes.
From microcontroller to microcontroller.
Do not try to parse your JSON inside a microcontroller. It's going to drive you nuts.
Oh, that's another thing That's something we may cover soon because I hope to able to cover programming. So let's see. But you do have when you do microcontroller level, chances is you won't be using high level data. You'll be in binary form and all that. I hope I have example. For that. You guys should go on UART first.
So especially for UART, this is where data structures are the most like useful because you're basically sending in data across like whatever you want to do, like whatever kind of data you want to send, right? There's nothing preventing you from sending whatever you want. Like you can send JSON if you want, ASCII encoded JSON, even UTF-8 encoded JSON if you're really into that. But that means you have like 8 bits per character, and then basically you can't say as much instead of like packing as much into your data structure with like shared understanding between both parties. So this first 4 bits will be about like your headers, next 4 bits will be the temperature, etc., and then that's the same information encoded on the other side. So this really, like the data structures that you might have studied before really pays well with regard to like if you're doing communication with these kinds.
Correct. So
yeah, if you want to send a true or false, just send 1 bit. Don't send TRUE or FALSE.
So this is actually the sample source code of the UART that we send to the Honeywell sensor. And we're not sending string, we're sending in binaries. I literally need to encode everything in hexes just to send the information out. Then I literally had to pack it into bytes just to use it. So yes, when you do microcontroller project, you are working on this level. You are not working on our usual thing where we stuff our bits as a string. We send like 4 bytes, then we unpack it. Just to give you an idea how it looks like, right? Yeah, I think it's a bit, when I started, I think it's a bit insane, but it is what it is because the machines are small, so they are not beefy like my GTX 1060, right? And all that. So yeah. So UART but UART is a more understandable protocol because you can actually use this is what you use when you actually when we use Arduino when we do some debugging. That's what we use. We actually use serial communication to debug, and sometimes I use machine for machine. So for example, again, my favorite sensor, this guy output UART. This guy output UART through this, right, to the connector. Then also, I think we covered the 3 one. Anything else you want to add before I go on?
No, so UART means universal asynchronous receiver transmitter. So what makes it asynchronous and what makes it receiver? I think receiver transmitter, maybe that we can explain that as well. Like I'd like.
Yeah, so it has multiple pins again, UART, but the most important pins are just 2, your TX and RX, right? So in that sense, the receiver and transmitter, there's a TX line and then there's a RX line. Right, so one is transmit and one is receive. What makes it asynchronous is that the fact that unlike SPI and I2C, SPI and I2C both have clock signals as one of the lines. Like for SPI is your clock, literally SCK serial clock signal, and then for the I2C is your SCL line, right? It's a clock. So they have clock information transmitted together with the data. Whereas for the UART, there is no clock being transmitted on the line. The data is just sent on the line, hence the word asynchronous. There's no clock. So this requires that both sides, the receiver and transmitter, to be pre-configured to run at the same speed. That is the requirement. Like if one side is sending at 9600 and the other side is receiving at 19200, then it's going to end up getting gibberish. Right? So you need to make sure both sides run at the same speed, which is sometimes not very easy because there can be potential for errors because to get 2 devices to run at the same clock is not easy because first of all, clocks are not the same. Second, the clocks need to be divided down. and the two devices, unless they are from the same manufacturer, same batch, whatever, if they're completely different families, they may have, one may be running at, let's say, a 25 megahertz clock. The other one is running at a 24 megahertz clock. And then you divide down with different devices values to get the clock down to 9600. But 9600 is a very weird number. Not a nice round, not a nice binary number or something like that. So you have to have some very weird divisor to divide the clock down. And when you divide down, you usually can't hit 960 exactly. It'll be 96 something something. And that something will give you a little bit of an error. So if the error is like within a few percent, 3%, 5%, it's usually okay. But if your error is quite large, you actually end up when you have a transmitter sending or receiver receiving, they may end up getting gibberish because they're sampling the line at the wrong time. Because there is no clock. The clock is not on the line. So you don't know when the signal is right or wrong. You sample according to your own internal clock. And the internal clock has to be in sync with the other guy's internal clock. I hope that made the thing clear.
And I guess you'd notice as well, Suimeng, right? Like many of the serial protocols, data protocols that you use with the sensors, they will always have a checksum at the end. They'll have a packet header and a checksum because that's just how serial works. You don't really know whether you've actually received it until you've received everything, and then you can actually confirm that you've received it correctly. Otherwise, you'll have to ask for it again or wait for the next package. And I think because it's a receiver-transmitter terminology, if you're the receiver, then that means you have to connect the transmitter to the other's receiver and the other's receiver to your transmitter.
Yeah, the lines have to be crossed, right? So one person's RX to the other guy's TX, and then the other guy's TX to your RX. Yeah, but you can do it is a full duplex protocol, so you can actually receive and transmit at the same time.
Which makes it, that RX-TX switch becomes really complicated because sometimes in the PCB silk screen, you'll see RX and TX, but they're trying to be helpful that they actually, this is where you put your TX. But I don't, why did you change it? I know what I'm doing. And so okay, that's why I'm not receiving anything because the RX is actually a TX of that microcontroller.
Always double check. But the good thing about the UART is that it's driven by the microcontrollers and it's usually a low power line. So even if you get it crossed, you won't kill anybody lah. Unlikely to kill anybody unless you connect it to a power line. Then
is this similar? Like you mentioned the negotiation. Is this similar to the dial-up negotiation where it starts from high and then until you get to 56 kilobits per second, for example?
Normally there's no negotiation in terms of the speed. Both sides just have to have an agreed speed to use. So if you buy a sensor and the sensor has a UART on it for you to communicate with the microcontroller, the sensor will tell you exactly what speed it runs at. So normally it's either 9600, it's 9.6 kbps or 19200 or 11520. These are the common speeds that the sensors would run at, right? So it is fixed. You don't really get to negotiate or choose a speed. No. Normally that's
okay.
So that's the connection one. And good news is your microcontroller should have all this ready, right? You have all this ready, and with this knowledge, and so how do you know what protocol
I'd say it actually depends on the microcontroller. Like many of the tiny 85s, for example, like 6-pin, very small microcontroller, you can use it for, well, it's great for NeoPixels because it's fast enough, but it doesn't have UART. Like it has, you can have SPI and I2C, it shares pins, so you can only choose one, but it doesn't have UART. You have to bitbang the UART. So it depends on the microcontroller.
Yeah, correct. So the first thing is check your spec. But chances is, if you're a hobbyist like me, you use Arduino, then we already have a standard. We already have a standard in a way that you have two UART, you have one UART, the rest is software UART, software serial. Then you have two I2C, one SPI. That's a standard that you get unless you use the Mega. So double check your specification is always part of your. It's actually part of your part of the thing when you buy it. Good thing about these nowadays, they got a lot of documentation. There's a lot of documentation on what you can do and what you cannot do. That's one. And a lot of these have the specification. So for example, they tell you this, use UART on 96 bulb. So if you look at this, they will tell you what you need. And also, when I say UART, it's mostly talking about the protocol being used. It's not actually about the connector, because connector is another thing. For example, you have a Groove connector, then you have some other connectors. But even that, it's not really that matter. Just get your specification. Then just before we end, I think we actually overwhelmed a lot of information, like where to get sensor. I put this on the website. How to communicate and whatnot, and where to get. So the next one, to make things easier, I actually suggest that you visit two places. One is the Element 14 community. The Element 14 community will contain a lot of the information, like how do you control certain type of hardware, and they will tell you the specification and how do you do it. So you're very likely, as a hobbyist, hobbyist point of view, you are more likely to use this sensor on your project, because a lot of this example already covers everything, and I mean it. So for example, you want to do TensorFlow Lite and control your camera with this, you already have this here on the Raspberry Pi. You want to build OLED and music player, you already have that. So there's a lot of example of this. And this is the basic one, IoT water quality sensor on Arduino. So I suggest that double check on Hexter.io or Element 14 community. And from there, you actually get some idea how to do things, and yeah, you don't have to come up everything yourself. So, and this is actually, somebody, the famous, the famous, sorry, distracted. And a lot of these are experience, so you don't actually have to use everything. Chances is you use like two things, right? And chances is I suggest that you focus on one thing at a time. So if you're interested on keyboard, focus on keyboard and everything around keyboard. Don't be like me, don't hog things like me. These are money sink, and it's a good thing that I'm single and I don't go out. But choose what you want to do. So for example, the only project that I have been successful doing is, again, the PM sensor. That is a project that is reasonably live until it's dead for reasons. Choose a project. So conclusion, get some idea. I suggest two sites here, Element 14 community, Hexter.io. Then find out the sensor. Chances is the community page would have the sensor being used already. Use that as a resource so that you know where you're going. Even if they don't have resource, a lot of these hobby sites would have all the specification on how do you do this, and they even provide you with a library, so you don't even need to write the library from scratch. And how do you connect all this? So once you have that, then you can start on project. Then arguably you should choose a microcontroller, which is a mistake because I should actually introduce a microcontroller first, but I want to whet your appetite. So yeah, I hope you guys have fun. And if you're interested to know more, go to engineersmind.slack.com. We are there, and some of us are actually working on hardware, and we can help you. So anything else? No. With that said, next week I think we're going to cover microcontrollers. I have too many. I have way too many. Then we're going to show you the how. Then I think that may be the last episode, because originally I thought of doing MicroPython, Arduino programming. It might take too long, so I think next week we're going to cover the microcontroller and then microcontrollers, then what's the framework being used and all that. Then yeah, hopefully you can get started from there. I hope. So anything else? If not, I'm going to say goodbye for reals. All right, goodbye guys. I hope you guys have fun. And I know for some reason YouTube didn't go live. I figured it out later. So goodbye. I hope you guys have fun with this and don't burn out your house.